For decades, we've searched Mars for the greatest secret in the cosmos. Was our neighboring world once alive? NASA missions have uncovered the undeniable truth of ancient water, rivers that carved valleys and smoothed ancient stones, but the search didn't stop there. Now, we're finding chemical traces like strange methane spikes and organic molecules. Are these signs of life or just geology? This is what Mars can tell us today, and why its ultimate secrets are still waiting. In this video, you will discover the most recent and credible findings from NASA's Mars missions. We will start with the evidence of ancient water, move to chemical traces that may point toward habitability, and end by explaining what unanswered puzzles remain. Clear graphics and straightforward definitions will help explain why these results matter for future missions, including returning samples to Earth. By the end of this video, you will have a clear sense of what Mars can and cannot tell us today. Signs Mars once held. Water. Was Mars once a planet where rivers wound through valleys and lakes filled basins rather than the dry, dusty world we see today? That question has been central to NASA's exploration of the planet for decades, because flowing liquid water not only reshapes a planet's surface, but also creates the essential conditions where life could, in principle, take hold. When orbiters began mapping Mars with high-resolution cameras, they revealed patterns carved into the terrain that looked strikingly familiar. Valley networks traced across the highlands, branching in ways that resemble watersheds here on Earth. Large fan-shaped deposits appeared at the mouths of craters, similar in shape to river deltas that form where streams meet standing water. These images suggested that, long ago, liquid water moved steadily across the Martian surface, cutting channels and depositing sediments. But right from the beginning, there was debate. Some geologists argued that the branching channels could be carved by lava flows rather than water. Because Mars is a volcanic planet with massive features like Olympus Mons, lava was a reasonable alternative explanation. Lava can run downhill, spread, and carve channels as it cools. For a while, these competing hypotheses created uncertainty. Were scientists really looking at rivers? Or were these formations a product of intense volcanic activity? The discussion changed when robotic rovers began examining Martian rocks up close. NASA's Curiosity rover, which landed in Gale Crater in 2012, found pebbles rounded in shape, sitting within old stream beds. These stones were not jagged or sharp, but smoothed, much like small river cobbles you could pick up from a stream back on Earth. That kind of smoothness happens when water pushes rocks along the bottom of a flow, rolling them again and again until rough edges wear away. This direct observation provided ground-level evidence that fluids once packed enough force to move stones across Mars' ancient landscape. On Earth, anyone who has walked along a riverbank can recognize how long-term flowing water turns rough rock fragments into polished surfaces. Seeing the same features captured by Curiosity tied Mars's past environment to something familiar and concrete. This was no longer an abstract idea, but a direct clue that strong streams once existed there. More evidence arrived from the Mars Reconnaissance Orbiter, which carries a detailed spectrometer able to measure the composition of minerals from orbit. Data revealed clay deposits scattered across many regions. Clays form in the presence of water through chemical reactions that alter volcanic rock. Their existence implied that liquid water was not just a brief event, but persisted in some areas long enough for chemistry to change the surface. Taken together, these lines of evidence pointed to a major shift in scientific consensus. Early Mars likely supported stable liquid water that lasted millions of years before it disappeared. The current hypothesis is that the planet once had a thicker atmosphere, allowing rivers and lakes to survive. Over time, though, much of that atmosphere escaped into space, leaving a colder and drier world. What remains today are traces, valley patterns, pebbles smoothed by ancient streams, and clays recording reactions from a wetter environment. This raises a larger question. If water endured for so long, did Mars cross into conditions suitable for life? Answering that requires more than showing water existed. It demands a closer look into the chemistry. the energy sources, and the possible biological processes that could have been sustained. What we can confirm now is that Mars's ancient landscape was habitable in principle. It had the raw ingredients and liquid water essential for life as we know it, even if no signs of biology have yet been detected. From here, the search moves beyond landscape and minerals. The next stage of exploration focuses on the chemistry of the planet, puzzling signals in its atmosphere and whether they represent natural geology or something more. Chemistry and the question of habitability. Mars has offered more than just landscapes shaped by ancient water. Beneath the surface, dust, and within the thin air, there are chemical signals that continue to spark curiosity. These signals are not direct proof of biology, but they are unusual enough that they call for closer study. NASA's rovers have measured molecules and gases that suggest the planet once had, or may still have, the raw materials needed for life to be possible. Each discovery adds a layer to the puzzle of whether Mars was ever habitable in more than just theory. One of the clearest findings came when Curiosity drilled into Martian rocks and detected organic molecules. In scientific terms, organics are carbon-based compounds that form the foundation for life on Earth. They can act as the building blocks of cells. Yet, it is important to be precise. These compounds can also arise from entirely non-living processes. A meteorite strike, for example, can bring in organics. They can also form through chemical reactions that have nothing to do with biology. The presence of organics on Mars is therefore exciting, but not decisive. It demonstrates that Mars holds some of the same chemistry we associate with living systems, while leaving open the origin of those materials. The reaction after this discovery was one of cautious interest. Many people heard organics and thought of microbes or fossils. Scientists, however, stressed that these results must not be confused with evidence of living organisms. The controversy mainly comes from the fact that the same carbon molecules that life depends on can appear without any connection to biology. This is why organics are called necessary but not sufficient. They are a basic ingredient, but on their own, they do not tell us whether life ever began or flourished on Mars. A second line of investigation has come from Curiosity's repeated measurements of the Martian atmosphere. Over time, the rover detected small amounts of methane, a simple gas made from one carbon atom and 4 hydrogen atoms. On Earth, methane is most commonly produced by living microbes and human industry, but it can also seep out of rocks through geological reactions. What caught researchers' attention was not just the presence of methane, but how its levels seemed to vary with the seasons. Sometimes the gas was more abundant, sometimes it dropped close to the detection limit. Explaining why this happens is difficult. Methane is unstable in Mars's thin oxidizing atmosphere and should break down fairly quickly, yet spikes keep appearing. That inconsistency has made scientists describe it as one of the most puzzling atmospheric signals measured so far. The mystery can be compared to walking through an empty building and hearing footsteps. There may be a natural cause, perhaps the wind shifting debris, but the sound still makes you pause. Similarly, methane does not prove life, but on a planet that once held water, it raises questions worth testing. NASA's Perseverance rover is now exploring Jezero Crater, a site chosen because it once contained a lake and river delta. Sediments there may have preserved biosignatures, which are chemical or textural traces left by biological activity, if it ever occurred. Rocks in this area are being drilled and stored in sealed tubes. The idea is that, if returned to Earth, they can be tested in laboratories with tools far more sensitive than what rovers carry. Perseverance is therefore a bridge between detecting unexplained chemistry and one day confirming or ruling out a biological origin. At this stage, the consensus is that Mars shows encouraging hints. With organics in the rocks, variations of methane in the air, and carefully selected samples now cached, the case for past habitability grows stronger. But none of this reaches the threshold of proof. Each clue has multiple possible explanations, geological as well as biological. The working hypothesis is that Mars had the right mix of chemistry, yet whether life ever took advantage of it remains unanswered. To resolve these uncertainties, scientists agree the next key step is sample return. Only when Martian rocks and soil are studied directly in controlled labs on Earth will these chemical puzzles be solved in detail. This is how the search for life on Mars moves forward, from intriguing chemistry today to the promise of clearer answers in the future. Conclusion. The consensus view is that Mars was once more Earth-like, with rivers, lakes, and long-lasting liquid water. Today, it holds chemical clues, such as organics and methane, but evidence of life remains unconfirmed. Mars shows habitability in principle, yet certainty has not been reached. A working hypothesis is that sampling Martian rocks directly on Earth will provide the breakthrough. NASA's planned missions aim to return sealed cores within the next decade. Until then, each new observation sharpens our picture of Mars's history. Following NASA's updates allows you to see how our understanding of planetary habitability steadily evolves.